So once again, welcome back to the study of RLC series circuits, which is fed by an AC generator, and I have just shown this in a simple manner. R, L and C. The current is the same in all the elements, and the voltage across R is I into R, and across L is omega L into I, and across C it is omega C into I, etc. Now, what we have applied over here is V is equal to Vm sine of omega t, as per what we have been taking in all the cases, and there is, this feeds to an impedance Z is equal to under root of R square plus Xc minus XL or difference XL whole square. Okay, so I can write the value of Im is equal to Vm upon Z. Okay, written like this, where XL is equal to omega L and Xc is equal to 1 over omega C. Now what happens is that this value depends upon the value of omega, and if what we do is that we choose a frequency omega is equal to omega naught such that XL is equal to Xc, then this cancels out, this becomes equal to 0. So Z becomes equal to under root R square, R is equal to R ohms. Okay, so Z is equal to R, and I can write the value of Im, the current, which will be the maximum value, Vm upon R. Okay, so omega L will be equal to 1 upon omega naught C, omega naught L, or omega naught square is equal to 1 upon LC. Very simple mathematics, sir. Omega naught is equal to 1 upon under root LC, or mu naught, which is equal to omega naught upon 2 pi is equal to 1 upon 2 pi under root LC. Okay. Now, if I plot a graph of Im in amperes, okay, naturally Im is equal to I root 2, okay, where I is the effective value or the RMS value, which is a measurable quantity measured with the help of simple instruments. Okay, sometimes the instruments are the galvanometer type, and sometimes the instruments are some kind of a thermal instruments which are also used. We have not talked about that, and we will not. Okay, just we don't want to confuse you. So look at this blue curve. First of all, Im is small, because at lower frequencies what you can see is that at lower frequencies this Xc value is large. Okay, and then naturally the value of Z becomes large. As we increase the frequency, so the Xc value it starts decreasing, and the XL value increases. That kind of a graph for this and this I've already done in the individual exercises of inductor and capacitor. So what happens is that when this value is reached, which corresponds to our frequency omega naught, then the current becomes optimum, the current becomes maximum. And thereafter, as the frequency is further increased, then the omega L value exceeds the 1 upon omega C value. And therefore again the value of Z rises. When the value of Z rises, then the value of the current becomes smaller. So there is a graph that we'll obtain, which appears to be kind of symmetrical, but it is not. So you can see that now we define a half power frequencies omega 1 nu 1 and omega t nu t. This frequency, the increased frequency omega 1 nu 1 is equal to omega naught plus delta omega, and this decreased frequency on this side is omega 2, which is omega naught minus delta omega. Correspondingly, we can have nu naught is equal to nu 1 is equal to nu naught plus delta nu, and nu 2 is equal to nu naught minus delta nu, etc., etc. Okay. Now, naturally, this frequency which has been shown here, okay, and this frequency which has been shown here, they are different. One is omega 1 is larger than omega 2, so omega 1 minus omega t will turn out to be equal to 2 delta omega. Okay. Now, suppose I say that the maximum value of power is equal to P, so half power will become equal to P by 2, and I can write it as Im maximum square upon 2 R, which I can write as Im by root 2 whole square into R. So this omega 1 and omega 2, they correspond to Im upon root 2, which is, for reasons I have explained you earlier, with root 2 I multiply in the denominator and the numerator, this becomes root 2 and this becomes 2. 1.414 divided by 2 gives 0.707 Im, or 70.7% of the peak value, which is obtained over here. Okay. So I have written these things, and we define the difference of these two half power point frequencies as the bandwidth. And we'll see in the due course of time that also I can write this as equal to Vm upon R root 2. Just divide by R and we'll get Vm upon R root 2. But Vm for a given value here is a constant, is already defined. So look here. If this is positive and negative, the current goes like this. If it changes, this becomes positive and this becomes negative, because this source is what? Vm sine of omega t. So this is sinusoid. So it will keep on changing. Sinusoidal wave. Harmonic oscillator that we have here, and therefore it corresponds like that. Well, there is a consideration of quality, okay, and I have two set of curves, 1 and 2. In one I have shown that the peak sharpens very beautifully, and here the peak sharpening is kind of blunt, so that the frequencies here for omega 2 and omega 1, they are more than this difference. So bandwidth is rather increased. Okay. We'll see in the due course of time. I'm not going to waste that for you here. That there is something known as the quality of a resonant circuit. The sharper the peak, the better the resonance. That we'll talk about shortly. Let's analyze it further. what we have, the equation, when omega is equal to omega 1, this frequency over here, okay, the higher of the two frequencies, half power frequency, omega 1 here, then I can write Im is equal to Vm upon R square plus 1 upon omega 1 C minus 1 omega 1 L whole square and the whole raised to the power of half, that is under root. And that is given as Vm upon R root. Okay. So when we compare this with this, we find that I squared this also, and find R square plus 1 upon omega 1 C minus omega 1 L is equal to 2R square, or simply 1R square will go with 1R square and this will be left R square on this side, and when we take the under root. Now I am writing, okay, see here, omega 1 L minus 1 upon omega C is equal to R, because we are talking about this frequency omega 1, and at this frequency the inductive reactance will be more than the capacitive reactance, okay, and therefore we'll write like that, okay. So I hope you understand that. And now I write omega 1 is equal to omega naught plus delta omega, and no omega 2, this only. So omega naught plus delta omega into L minus 1 upon omega naught plus delta omega into C is equal to R. Let me take omega naught out of the bracket. What I get? Omega naught L 1 plus delta omega upon omega naught, and minus over here. Similarly, I take omega naught out, so omega naught C 1 plus delta omega upon omega naught. This is equal to R. Like that. Now we have omega naught square is equal to 1 upon LC with the condition of resonance and of the resonance frequency. So from here we see that omega naught C is equal to 1 upon omega naught L, or 1 upon omega naught C is equal to omega naught L. If I substitute that, okay, then 1 upon omega naught C, this becomes equal to omega naught L, and for this in the denominator I can write it as 1 plus delta omega upon omega naught raised to the power of minus 1. Okay. Then I make a binomial expansion. Okay. And the higher order terms we take as equal to 0. So this becomes equal to 1 minus delta omega upon omega naught. Okay. So I have 1 plus delta omega upon omega naught minus 1 minus delta omega over omega naught, and so I can write, okay, I can write, so we did write that omega naught L 1 plus delta omega over omega naught minus omega naught L. Now this is because 1 upon omega naught C is taken as omega naught L, and this expression over here is taken as 1 plus delta omega upon omega naught raised to the power of minus 1 is equal to R. Now I expand it binomially, take the linear approximation, and all higher order terms are ignored because delta omega upon omega naught is very small, okay, normally small. So I can write this term over here as 1 minus delta omega upon omega naught, okay, and use it here. Now when I put it back in this original equation, I get omega naught L, and here also we have got omega naught L, so I'll take that out of the bracket. So I'll get 1 plus omega delta omega upon omega naught minus this quantity, which will become minus 1, plus delta omega upon omega naught, which is equal to R. So you can see that 1 and 1 will cancel. Omega naught will also cancel with omega naught, and I'll get 2 delta omega is equal to R upon L. And 2 delta omega was defined as bandwidth. Anyway, so I can write delta omega is equal to R upon 2L. Right? Now, the sharpness of resonance, that is defined as the quality factor of, because we saw that the quality factor in the first one is better than the quality factor in the second one. So Q becomes equal to omega naught upon the bandwidth 2 delta omega. So I can write this as omega naught, because delta omega is equal to R upon 2L, etc. So we'll get is omega naught L upon R, which is XL at the resonance frequency divided by R. And similarly, we can have the quality factor defining that omega naught square is equal to 1 upon LC. We can substitute that and we find that the quality factor or the sharpness of resonance is also given in terms of omega naught 1 upon omega naught RC or CR. Okay, so this one and this one, they have their correspondence. Now, one thing, that the resonance will be obtained only when L and C both are present. Okay? The R will be a deciding factor, of course, for the current, and this kind of circuit is used, the resonant circuits are used for the purposes of tuning, and in particular they can function at audio frequencies, also at radio frequencies. So at radio frequencies, which are very large frequencies as compared to the audio frequency range is 20 Hz to 20,000 Hz, and the radio frequency is much larger. So then we used to have a beautiful equipment once upon a time, which was called a AM radio. Amplitude modulation system was used. Okay, and the price of the radio, you will be surprised to know that the price of the radio when I was a kid and the price of the radio today, after having fallen from that price, is almost the same. I belong to the upper middle class, but anyway, it took about 2.5 months salary for my father, who was a magistrate at that time working in the UP Revenue Department, to buy a radio, and the company's name was Pi. What is pi? 3.14. Okay, no. It's the ratio of the circumference to the diameter. So, the amplitude modulated radio, when it was acquired in our house, in our village, then we had some very funny things associated with that. One was earthing, about 8 to 9 feet, and copper plates were put there, and then there were antennas. We had a double story on this side, another double story on this side. So at that time we used to have bamboos. The 2 bamboos were tied together very tightly, and the antenna was put there, and there was only one radio station which used to cater, and that was the radio station from Lucknow. Okay, but shortly another radio station popped up in Allahabad, so it was Lucknow, Allahabad. Okay, and there we had to tune in, and the tuning was done naturally, because this frequency omega naught or nu naught or whatever you have, this is obtained as a square of it, we obtain with the 1 upon LC. Okay, L and C. Look here. So either to tune to from one station to another station, either we had to change L or we had to change the C. Okay, changing L was a difficult proposition. 3 or 4 inductors used to be there in the radio circuit. But capacitor, of course, what we can do, you can see that the capacitor theory is like this. This is the one plate of the capacitor, and this is the other plate of the capacitor. How much is the capacitance? C is equal to epsilon A over D. Epsilon A over D. And if you don't subscribe to that, then I'll write epsilon naught A over D, but there never used to be any vacuum created over there. Air was there, and almost epsilon naught for air and this epsilon were the same. Now what I can do, okay, what I can do is that I can change the effective area. How? I can reduce the area, I can enhance the area, and there used to be a capacitor in which the surface area used to go like this, okay, like this, and so they will change the area, and the capacitance will change, and the value of 1 upon LC will change, and therefore the frequency that is tuned will change. These days, instead of radios, you have television, but you have an infrared control system, digital system, by which you can just change the radio stations. Plenty of them are there. Okay, so this is called tuning, and fine tuning used to be there, and then we used to have bands of frequencies, long wave, short wave 1, short wave 2. We'll have occasion to talk about it sometime. Thank you very much for the day.